NENOMATICA, where mathematics meets YouTube excellence. Exponential inequalities. Welcome to our lesson on solving exponential inequalities. Today, we'll learn how to solve a special type of exponential inequalities involving 3 different bases. Let's begin by understanding the general form of these special exponential inequalities. We have alpha times a raised to the power of f of x, plus beta times b raised to the power of f of x, plus gamma times c raised to the power of f of x is greater than or equal to 0. Or, alpha times a raised to the power of f of x, plus beta times b raised to the power of f of x, plus gamma times c raised to the power of f of x is less than or equal to 0. For these inequalities, there are some important conditions where alpha, beta, and gamma are non-zero real numbers. A, B, and C are 3 different positive bases, and f of x is a function. When these bases form a geometric progression, meaning they have a constant ratio between consecutive terms, these inequalities can be transformed into quadratic inequalities. Let's understand what it means for A, B, and C to form a geometric progression. A geometric progression is a sequence where each term is found by multiplying the previous term by a fixed, non-zero number called the common ratio. For bases to form a geometric progression, if b divided by a equals r, then c divided by b must also equal r. This means that b squared equals a times c, which is the key condition that allows us to transform these exponential inequalities into quadratic inequalities. Let's understand how we transform these exponential inequalities into quadratic inequalities. We'll make a substitution. Let y equal a raised to the power of f of x. Since b raised to the power f of x equals a raised to the power f of x times r, we can substitute this as y times r. Similarly, c raised to the power f of x equals a raised to the power f of x times r squared, which we can substitute as y times r squared. To make things clearer, let's denote our raised to the power f of x as t. Now we have y equals a raised to the power of f of x, b raised to the power f of x equals y times t, and c raised to the power f of x equals y times t squared. Now let's substitute these values into our original inequality. We get alpha times y plus beta times y times t plus gamma times y times t squared is greater than or equal to 0. Since y is equal to a raised to the power of f of x, and a is positive, y is always positive. So we can factor out y from our inequality. This gives us y times open parenthesis alpha plus beta times t plus gamma times t squared close parenthesis is greater than or equal to 0. Since y is always positive, we can divide both sides by y. This means alpha plus beta times t plus gamma times t squared is greater than or equal to 0. This is a quadratic inequality in terms of t. Let's walk through an example to see how we solve these types of inequalities. Solve the inequality 2 times 3 raised to the power 2x plus negative 5 times 6 raised to the power 2x plus 3 times 12 raised to the power 2x is greater than or equal to 0, where x is a real number. First, let's check if our bases form a geometric progression. We have a equals 3, b equals 6, and c equals 12. So b divided by a equals 6 divided by 3, which is 2, and c divided by b equals 12 divided by 6, which is also 2. We can also verify that b squared equals a times c. 6 squared equals 36, and 3 times 12 equals 36 as well. So, our bases do form a geometric progression. Welcome to our math lesson today, where we're going to dive into the world of exponential inequalities. Let's start with an example that will help us understand how to solve exponential inequalities. In this inequality, we need to solve for x. Let's start by rewriting our expression. We notice that 7 squared is 49 and 20 squared is 400. So we can rewrite our inequality as 3 times 49 to the power of x plus 37 times 140 to the power of x is less than or equal to 26 times 400 to the power of x. Now, let's identify the coefficients in our quadratic-like expression. We can see that it equals 49, b equals 140, and c equals 400. Let's continue by dividing both sides of the inequality by 400 to the power of x. This gives us 3 times 49 to the power of x divided by 400 to the power of x, plus 37 times 140 to the power of x divided by 400 to the power of x, minus 26 times 400 to the power of x divided by 400 to the power of x, is less than or equal to 0. Now we can simplify these fractions. This gives us 3 times 49 to the power of x over 400 to the power of x, plus 37 times 140 to the power of x over 400 to the power of x, minus 26 times 1 is less than or equal to 0. We can further simplify by expressing the fractions as powers. We get 3 times the quantity 49 over 400 to the power of x, plus 37 times the quantity 140 over 400 to the power of x, minus 26 is less than or equal to 0. Let's simplify these fractions further. 49 over 400 equals 7 over 20 squared, and 140 over 400 equals 7 over 20. So our inequality becomes 3 times the quantity 7 over 20 squared to the power of x, plus 37 times the quantity 7 over 20 to the power of x, minus 26, is less than or equal to 0. To simplify our work, let's make a substitution. Let t equals 7 over 20 to the power of x. Then our inequality becomes 3 times t squared plus 37t minus 26 is less than or equal to 0. Now we can solve this quadratic inequality by factoring. We get the product of t plus 13 and 3t minus 2 is less than or equal to 0. For a product to be less than or equal to 0, either one factor is negative and the other is positive, or both factors are 0. Since t equals 7 over 20 to the power of x, and this is always positive for any real value of x, t must be greater than 0. This means t plus 13 is always positive, so 3t minus 2 must be less than or equal to 0 for the inequality to be satisfied. Solving 3t minus 2 less than or equal to 0, we get t less than or equal to 2 over 3. Now we substitute back our expression for t. This gives us 7 over 20 to the power of x is less than or equal to 2 over 3. To solve for x, we need to take the logarithm of both sides. Since 7 over 20 is less than 1, and we're dealing with an inequality, we need to be careful with the direction of the inequality when taking the logarithm. Taking log base 7 over 20 on both sides, we get x is greater than or equal to log base 7 over 20 of 2 over 3. Therefore, our solution set, which we'll call D, is the interval from log base 7 over 20 of 2 over 3 to positive infinity. To summarize, when solving exponential inequalities, we start by rearranging to get a standard form. Then, we often make substitutions to convert the exponential inequality to a polynomial inequality. After solving the polynomial inequality, we substitute back and use logarithms to find the solution for the original variable. Remember to be careful with the direction of the inequality when taking logarithms, especially when the base is less than 1. Today we'll learn about solving a particular type of nonlinear inequality using a clever substitution technique. This approach allows us to transform a complex inequality into a simpler form. Let's examine the general form of our inequality. We have alpha times a to the f of x, plus beta times b to the f of x, plus gamma is greater than or equal to 0. Here, alpha, beta, and gamma are real numbers with alpha not equal to 0. The values a and b are positive numbers that are reciprocals of each other, meaning a times b equals 1. When facing this type of inequality, we can use a clever substitution to simplify our work. We define t equals a to the power of f of x. Since a and b are reciprocals of each other, meaning a times b equals 1, we can express b to the power of f of x in terms of t. If t equals a to the power of f of x, then b to the power of f of x equals 1 over t. Now, let's apply our substitution to transform the original inequality. We replace a to the f of x with t, and b to the f of x with 1 over t. This gives us alpha times t, plus beta times 1 over t, plus gamma is greater than or equal to 0. Notice how our inequality has been transformed into a much simpler form involving t and 1 over t, which is a rational function of t. Let's solve this rational inequality step by step. First, since t is positive, because it is positive and t equals a to the f of x, we can multiply both sides by t without changing the direction of the inequality. This gives us alpha times t squared, plus beta plus gamma times t is greater than or equal to 0. Step 2. Let's rearrange to the standard form of a quadratic inequality. We get alpha times t squared, plus gamma times t, plus beta is greater than or equal to 0. This is now in the form at squared plus bt plus c is greater than or equal to 0, where a equals alpha, b equals gamma, and c equals beta. Step 3. Now we can solve this quadratic inequality using standard methods. We find the roots of the corresponding quadratic equation, and then determine. Let's illustrate this technique with a concrete example. Consider the inequality. 2 times 3 to the x minus 5 times 1 over 3 to the x plus 3 is greater than or equal to 0. Here, alpha is 2, a is 3, beta is negative 5, b is 1 over 3, which satisfies a times b equals 1, and gamma is 3. The function f of x is simply x. Let's apply our substitution technique. We define t equals 3 to the x, then 1 over 3 to the x equals 1 over t. Substituting into our inequality, we get 2t minus 5 times 1 over t plus 3 is greater than or equal to 0. Multiplying both sides by t gives us 2t squared minus 5 plus 3t is greater than or equal to 0. Rearranging to standard form. 2t squared plus 3t minus 5 is greater than or equal to 0. Now we solve the quadratic inequality 2t squared plus 3t minus or equal to 0. Now we solve the quadratic inequality 2t squared plus 3t minus 5 is greater than or equal to 0. Let's find the roots by solving 2t squared plus 3t minus 5 equals 0. Using the quadratic formula, we get t equals fraction with negative 3 plus or minus square root of 9 plus 40 over 4, which simplifies to t equals fraction with negative 3 plus or minus square root of 49 over 4. Further simplifying, we get t equals negative 3 plus or minus 7 over 4. So our roots are t equals 1 and t equals negative 5 over 2. Now let's analyze when the quadratic expression 2t squared plus 3t minus 5 is greater than or equal to 0. Since the coefficient of t squared is positive, the parabola opens upward. This means the expression is non-negative when t is less than or equal to negative 5 over 2, or when t is greater than or equal to 1. However, recall that t squared is positive. The parabola opens upward. This means the expression is non-negative when t is less than or equal to negative 5 over 2, or when t is greater than or equal to 1. However, recall that t equals 3 to the x, which means t must be positive. Therefore, we must restrict our solution to t is greater than or equal to 1. Now, let's convert back to our original variable x. From t equals 3 to the x, we can solve for x by taking the logarithm base 3 of both sides. This gives us x equals logarithm base 3 of t. Since we need t is greater than or equal to 1, we get x is greater than or equal to logarithm base 3 of 1, which is 0. Therefore, the solution to our original inequality is x is greater than or equal to 0. Let's summarize the substitution technique for solving this type of nonlinear inequality. Step 1. Identify the form. Let's start with our example. Here we have an exponential inequality to solve. Let's start solving this step by step. First, we'll rewrite the second term as a fraction with the same base as the first term. Notice that 10 to the power of 1 minus 7x is equivalent to 1 divided by 10 to the power of 7x minus 1. To simplify this inequality, let's make a substitution. Let t equal 10 to the power of 7x minus 1. This substitution will convert our exponential inequality into a quadratic inequality, which is easier to solve. Now, to eliminate the fraction, we'll multiply both sides of the inequality by t. Since t is 10 to the power of 7x minus 1, it's always positive. So multiplying by t doesn't change the direction of the inequality. We now have a quadratic inequality. T squared minus 5t plus 6 is less than or equal to 0. Let's solve this by factoring the quadratic expression. For the product of two terms to be less than or equal to 0, either one term must be negative and the other positive, or both terms must be 0. Since t is always positive, we can find our solution from the factors. From our factorization, t minus 2 is non-negative when t is greater than or equal to 2, and t minus 3 is non-positive when t is less than or equal to 3. Combining these conditions, we get that t is between 2 and 3 inclusive. Now that we have our solution for t, let's substitute back our original expression. T equals 10 to the power of 7x minus 1. So our inequality becomes 2 is less than or equal to 10 to the power of 7x minus 1, which is less than or equal to 3. To solve for x, we need to isolate it. Since x is in the exponent, we'll take logarithms of all parts of the inequality. Since we're working with base 10, we'll use the common logarithm. Next, we'll apply the logarithm power rule, which states that the logarithm of a number raised to a power equals the power times the logarithm of the number. So, log of 10 to the power of 7x minus 1 equals 7x minus 1 times log of 10. Since the logarithm base 10 of 10 equals 1, our inequality simplifies to log of 2 is less than or equal to 7x minus 1, which is less than or equal to log of 3. Now we can solve for x by adding 1 to all parts of the inequality and then dividing by 7. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.